Awesome, thank you. What a wonderful introduction. And then do we have mine? Perfect, cool. All right, great. That's me. I'm here. We're going to talk about Istio. We do not have a lot of time, and this is already a tight talk, so let's get going. Real quick, by show of hands, who has heard of a service mesh before? All right, who's heard of Istio specifically? Who's used it? All right, awesome. So here's the whirlwind tour, right? The basic setup that we have, as ever, is two services want to communicate. We don't really care what this communication is. It's happening over the network. It could be HTTP, it could be SQL, Redis, whatever the protocol is. But these two services need to communicate. The first thing that we do when we're building this service mesh is drop a proxy in beside every application. The particular proxy that Istio uses is called Envoy. And we picked it because it's tailor-made for this use case. It's made for, with a lightweight footprint. It's made to be dynamically reprogrammed at runtime. You don't have to do things like restart it to get configuration updates to take effect, that kind of stuff. And we put it in the same trust domain as the application. So if your application was running in a VM, you would put this proxy in the same VM right next to the other process. If you're in Kubernetes, it goes into the same pod, right? And this is a very important point. It's in the same trust domain because that proxy is actually going to be what gives us identity at runtime and a bunch of other cool things besides. So you have these Envoy proxies, and they can do a whole bunch of stuff for us. We'll talk about the feature set that they provide, but things like resiliency, visibility into the traffic that actually flows through the system, and the ability to apply policy to that traffic. But just having an Envoy there doesn't do you any good. You need to actually program it to make it functional. And so we say, we call Istio's control plane the components that are responsible for programming those envoys at runtime. The first piece of which is called Galley, and it's responsible for configuration distribution. So you can imagine if you have, like any network controller, if you have an SDN, you have a network controller, you have to be very careful about the configuration that you push to that network controller. By the same token, in Istio, we're kind of acting as the network for your applications. It's not that hard to push configuration that can cause network outages, right? It's pretty easy to disconnect yourself from the network and things like that. Therefore, Galley exists as a component that actually is aware of Istio's own configuration and some of the semantics, so it can do things like safely roll out and update across Istio's components. For example, I want to push a networking config. Maybe it's going to take out part of the cluster. I don't know. I would like for that to be rolled out in a controlled way, incrementally across my deployment, one control plane instance at a time. Galley is precisely the piece that does that. So having configuration is fine, but things need to consume that configuration. The first piece that we'll talk, or the next piece that we'll talk about, is a component called Pilot. And Pilot is really kind of where the rubber meets the road. So Envoy is highly dynamic, highly programmable. Pilot is the piece of Istio that implements those APIs, that programs Envoy to implement behavior. So you can think of Pilot as taking an understanding of the topology of your deployment. Right? If you're in Kubernetes, it knows all the services and all of their endpoints, what ports they're all listening on, right? It understands the network topology. It understands the configuration, the Istio configuration that you've written. It takes both of those together, and it builds a model of your deployment. And then it uses that model to generate configuration for envoys at runtime so that they actually implement the behavior that you configured, right? I say I want to retry. Pilot goes and actually produces the Envoy configuration to make sure that that Envoy performs retry for you at runtime. Next, we have what's called Mixer. Mixer is a little bit interesting because in some ways it's part of the request path. So Mixer fulfills two primary roles. The first is telemetry generation. So as requests flow between envoys, they gather up data about that request. How long did it take? Where did it come from? If it's HTTP, what's the response code? Right? All the good stuff that we just, if we're an application level proxy, we know. And it reports it back to Mixer asynchronously and out of band. With that, Mixer excuse me, with that, Mixer produces metrics that it sends to other metrics backends, right? So for example, if you're running, in the demo that I'll show you, we have a Prometheus running, and Mixer's getting scraped by Prometheus to produce metrics that describe traffic through the entire deployment. The other use cases for policy. So there's all kinds of policy that I want to implement about traffic in my system, right? For example, it's pretty common that I want to do abuse classification. I want to do rate limiting is a form of policy. I want to control which services talk to which other services, right? I want to update my network security posture from one that's a perimeter-based model to one where we're actually like controlling who talks to which two pairs of services get to talk anywhere in my deployment, right? All of those types of policy about traffic and about how services are allowed to communicate go through Mixer. In some ways, Mixer is kind of an extension to Envoy that's out of process and a little bit easier to manage. And then the final piece for us to talk about is a component called Citadel. So I would argue that identity is the fundamental underpinning of all communication. And it's especially important when we talk about service communication or machines communicating. Up until now, largely the state-of-the-art around identity and for machine security is IP ports, right? I have a network. If you can call that machine on that port, then you are authorized to have access, right? Reachability is authorization. That doesn't work in a newer world that's dynamic, right? As we're building these container-based services and Kubernetes likes to move things around and change IP addresses and do things like that, that starts to fail. I need an identity for my workload, for my service, that's not tied to where in the network it's located, but what it actually is. And so Citadel is responsible for minting identities that it gives to an Envoy. That identity is a certificate, the same kind of certificate that you would use for normal HTTPS termination. But critically, that certificate encodes the name of the workload. And so at runtime, when two services communicate, they can use mutual TLS, where both sides give their certificate to each other. We do our normal TLS validation. You do one additional step of validation according to a specification called SPIFFE. And out of that connection, you get an authenticated identity. I know for sure the service on the other side, and I've authenticated that. Therefore, I can use that identity to apply policy. I can decide whether I allow that communication or not. And critically, both sides have that. So it's not just the server that's applying it. You can actually do this client side too. The client knows the server identity, and it could refuse to talk to a server as well if it chose to. And so together, we call these four components the control plane, and we call the envoys in the deployment that are actually handling the bits and bytes of requests, we call the data plane. So let's go back. So I opened this up with we have a hypothetical call from A to B, and let's just track that through the system end to end real quick. So the first thing that happens is the local envoy by A is going to intercept that traffic. There's a bunch of different mechanisms that it can use to do that. The most common today out of the box in an Istio installation, we use IP tables to intercept this traffic. But you can use BPF. You could update your application to talk to Envoy on localhost. There's any number of ways that you can do that. However you choose to do it in your deployment, Envoy gets the traffic that is outbound from A. And there it gets the opportunity to make a client-side load balancing decision. So Envoy, this Envoy that receives that request, doesn't care about the IP address that A sent. Right? If I understand the protocol, if I understand that you're sending an HTTP request, I don't care the IP address that you resolve to send it to. I'm going to look at the host header, because that host header is the service that you're trying to contact. And Envoy effectively at runtime does a little reverse lookup, says, oh, this host corresponds to this service that I know about, and that service has these 15 endpoints. I'll make a decision to send it to one of those 15, for example. However, and so Envoy picks some destination. This is really powerful, this client-side load balancing, because it means that we have a much more reliable system and we don't need these middle load balancers everywhere. Clients can actually act on data. If I'm calling a service and it's giving me bad results, I can just choose not to call that endpoint anymore. I can remove that outlier from my load balancing set and I can just focus on the ones that are giving me good responses back. This kind of functionality, but you can get that actually piecemeal between clients and servers rather than having some central proxy that's having to do this management and eviction. The end result is a much more reliable system overall. So this A is client-side envoy picks a destination and it forwards that request. It doesn't even necessarily know that there's an envoy on the other side. It doesn't really have to care. There is in this case, and so that envoy grabs the request that's incoming to B. Again, the same capture mechanism, and it talks to Mixer to get a policy decision. And Mixer will either give a thumbs up or a thumbs down. If Mixer gives a thumbs up and allows the request, then Envoy will forward it back into B. If Mixer said thumbs down, no, this request is not allowed, Envoy will just drop the packet on the ground. And then B does whatever it has to do, whatever I need to do to assemble my response. If that's calling other services or reading a database, or if it's just cache in memory, whatever it is, we get our response and we hand it back. And then both of them, asynchronously and out of band, report back their view of that interaction, both client and server. In more recent versions of Istio, we actually drop half of this. We only report the server side rather than reporting both, just because the metrics most of the time are nearly identical, but you're just doubling the volume that you're storing. There are some use cases where it can be valuable to have both sides, in particular if you're trying to get to the bottom of interesting or sticky networking problems. So in a slide, this is Istio's architecture. There are these 5 major components: Envoy, the data plane; Pilot to program it; Mixer to provide telemetry and policy; Citadel to provide identity; and Galley to configure everything else. So I didn't actually spend very much time talking about what it does. These are some of the key features that a mesh can give you. So because these Envoy proxies are intercepting all the traffic, and because they understand the protocols that you're using, we can do things like layer 7 load balancing, right? Per request load balancing, deciding which destinations a request goes to per request, right? I can do things like matching on headers or user agents or just percentage-based traffic splits even. I can do things like automatic retries, circuit breaking, and outlier detection, right? Stopping calling bad endpoints automatically. And all these things together mean that your system can actually be a lot more reliable. It handles jitter in a lot more healthy way than it might if you weren't programming with these things. On the visibility side, right, we can get metrics logs, and we can help propagate trace data through the system, right? So Adrian gave a talk earlier today about some of the benefits of tracing, and talked a little bit about some of the things you have to do to get it. There's no magic bullet. Istio can help you establish trace context and can propagate that into your application. If your applications will correctly propagate trace context out, then Istio will help annotate the full trace for you, right? And will help generate that and populate that with Envoy's view of the world and Mixer's view of the world as well. And of course, you can use this data to draw topologies of your deployment in real time. This is one of the most compelling things, right? When a new engineer joins my team, the very first thing that we sit down and do is we go to a whiteboard and we draw boxes and arrows, right, to describe here's the architecture of the system. It's much more compelling if you can just show it for real, like in a live system. I could just go to a dashboard and open it up and I say, this is what the system is right now. It's much more powerful. And then security is critical, right? So runtime identities for every single service. Having those identities means that I can write policy that's transferable, because it's not policy about a particular network topology. It's not policy, it's not this subnet can talk to that subnet. It's these two services can talk. Now suddenly I don't necessarily care where that service is, because where it is or where it's located or running is not part of the policy around what it can communicate with. Or it doesn't have to be part of the policy, which is it's a big game changer. And then as a side effect out of having these identities at runtime, you also get encryption in transit. That's a pretty valuable side effect in and of itself, but it actually is kind of a side effect of the system and not necessarily the primary end. And then maybe the single most important part is that all this is consistent across the fleet, right? So these are not one-offs. The metrics that your service is producing, that's not every individual application developer went and added metrics, and I hope that they added the right 5 dimensions, and that those 5 dimensions are populated the same way so that they have the same semantic meaning. No. A single team, for example, that owns observability across the platform can mandate that these are the metrics that are appropriate for us to gather. And we can ensure that they're gathered consistently across every single service. The same for logging, right? We can have standard logging everywhere. I can start to enforce standard security controls because I can start to write this policy based on these identities. This is the real crux of the benefit of the mesh, is that we get consistency and centralized management with the ability to delegate some of that management to individual teams too. Right? I can say, hey, application teams, you can write how traffic flows into your service and flows out to other services, but I'm going to write the security controls. Right? You don't get to touch the security parts of the Istio configuration, but you can have at the traffic parts, for instance. So with that just super fast introduction, what I want to do is run through a real quick demo of a more advanced use case. So this is, I think in the abstract, I think I list 3 use cases to talk through. Just in the to save time, we're only going to have time to cover one. And so the one that I wanted to talk about was active passive HA. So this is an actual customer that we helped. They had done maybe the hardest part of setting up an HA deployment, which is they had already migrated to a cloud provider database. So from our perspective, from the perspective of their applications, the database is effectively global. That makes our lives substantially easier, because effectively now all that I have to do to get an HA deployment is just stand up another copy of their cluster, and as long as we can control how traffic flows between the two of them, we can route around failures, right? And Istio makes it relatively easy for us to set up routing basically any way through this system that we might need to. And so really the takeaway here I want you all to see is how we can use the way that Istio creates and manipulates names to control how traffic flows through our system. Alrighty, so as a little bit of context, I have 2 Kubernetes clusters that are up and running. And if we look, we can, sorry, let me make sure that's, yeah. And if we look, I have in both of these clusters, if we ever, there we go, okay, perfect. I just have a front end and a back end server running. If we notice that ready 2 out of 2 is maybe a little bit atypical. Typically you would only see 1 container in a pod. That's my front end or back end server, plus the sidecar would be the second container in that pod. And if I look in here, we can see, and we can see that I have a normal Istio deployment. This is actually just the demo Istio installation. And if we look, we can also go back to a secondary cluster, and it's materially the same. The same front and back end server are running, and the same Istio installation is running there as well. Critically, these have a common root of trust. So I set up ahead of time, I made sure that when they issue identities, these certificates that the services use at runtime, they actually have a common root so that we can communicate across. Alrighty, so what is the actual system that we have? We can, sorry, let me do a little bit of prep work here. Right, so those are my 2 load balancer IP addresses to get to the ingress to my 2 clusters. And so here I can say the HTTP command, for those of you that are not familiar with it, it's basically just a glorified curl. It just looks a little bit prettier. Can everybody read that fine in the back? Do I need to make it larger? All right, how about now? Yeah, good, excellent. So we're going to use HTTP for most of these instead of curl. It's the same. One thing to note here is I'm setting a host header specifically. This is just so I can do some routing, right? I'm using IP addresses to contact these load balancers. Host names are a little bit nicer for some of the Istio things we're going to do later. So I'm going to go ahead and set a host header as if I was using DNS to resolve this ingress IP address, right? And so our front end service has a nice little echo endpoint, and it tells me critically which cluster it was in, right? So we have front end.primary. Let's see if I can type. And if we call the secondary one, we see that's secondary, right? And so this is the easy way that we're going to identify which instance we're going to talk to. Every time we talk to an instance, it's going to tell me which cluster it's in. All right, excellent. So we have this front-end service. The other critical thing that we have is an endpoint to call. So when I call this endpoint on my front-end server, whatever the data that I give it is, in particular, in this case, this neverssl.com, it's going to turn around and just make a call, an HTTP call to that endpoint, right? So here we say, hey, the front-end primary server, it turned around and it called and it got this response. All right, so with this now, we can actually just do communication between our services in the deployment, and we'll see who's calling what and where. Whoops, sorry. And so to start with, we can actually just call the service that's local to our cluster, right? So we're talking to the front-end service. I can just call the back-end service like it's a normal service in Kubernetes. And here I see the front-end primary server called the back-end primary server. Great. And of course, the same works over here too. Secondary calls secondary. So where things get a little bit more interesting, and of course we can use a fully qualified name too. Now, for the people that were very, very astute, when I showed you this deployment, there is one piece here that is not typical of an Istio deployment, which is this core DNS server. So if I want to enable communication between two clusters, part of the problem in Kubernetes today is that service name is bound to a cluster. But if I am going to be doing routing across clusters, I need a name that spans clusters. So we're using a core DNS plugin with Istio. When I create a service entry in Istio, which is how I create a new service, this core DNS plugin creates a DNS entry for me. Right? Kubernetes does this out of the box. When I create a Kubernetes service, it creates a DNS entry. This is just doing the same for Istio. But there's one little catch, which is it's only looking for, it's only looking for, let me find the right thing to show you here. This .global endpoint. So this is a little config map that tells Kubernetes, hey, when you see a DNS query for .global, forward it to my core DNS server. Forward it to mine so that I can answer it with the Istio query, rather than you trying to answer it with, you don't know what that DNS entry is. Okay, so we have a little bit of DNS, so anything with .global is going to be resolved specifically by Istio. So now I can actually use this to start to do failover across clusters. If, for example, I take, let me find my, sorry about this, here we go. I can, for example, force traffic to fall back from my local backend to the global one in my cluster by pushing a small virtual service like this, right? So this just says, hey, if you see the host backend default, right, the normal Kubernetes service, send it to the global version. And we can go ahead and call this. We'll go ahead and apply this, sorry. We'll make sure we're in the right cluster. We'll go ahead and apply the rule. Oh, you're kidding me. Sorry, 1 second. This is the demo magic. Okay, that's good. Back into secondary. Back into secondary. Sorry. Always fun. Can't validate the certificate. This is actually me talking to my cluster right now. Sorry. This is kubectl being bad. Is it? Yeah, excellent. Sorry, I think this is actually me losing internet connection because I'm on the conference Wi-Fi. 1 second, this is, sorry. We'll verify with never SSL. There we go. Whew, okay. All right, not going insane. Okay, excellent. Did that. Sorry, we're almost there. And now we can take this call that we made to our backend service, and we're going again into the primary cluster, and I can see that it directly hit the secondary backend server, right? So we just did cross clusters like that, right? All I have to do is apply the config, and immediately I can flip-flop routing. And of course, this doesn't affect the secondary cluster, right? Because I only applied this configuration in one place, so it's not going to affect the other cluster, right? So I can do things like drain per cluster. And of course, we can do this at ingress too, right? It's not, this is still hitting the front-end server in my primary cluster. What if the front-end server is bad? I want to be able to kick over traffic at the ingress to my cluster, right? Before it hits anything inside the cluster itself. I can use a rule that's almost identical to before, right? Here's that host name that we've been calling. And it just says, hey, on my gateway, on my front end, if you see traffic for cns.istio.demo, send it to the global version. And just like before, we can apply. And we can see that, hey, even though I'm calling the primary cluster, I actually only ever hit services that reside in the secondary cluster, right? So we've actually managed to cover every single case here of failover between this set of services. Every combinatoric that we could have to successfully route traffic through the system, we've actually done. One thing I didn't mention, by the way, is all of this communication between clusters is secured with mutual TLS. There's no VPNs. There's no direct connectivity between the pods. We go out an egress proxy. We go in an ingress proxy. It's secured the entire way. And we can even do things like load balancing to specific subsets across clusters. If you have version 1 and version 2 deployed everywhere, I can make sure that when you call version 1 in one cluster and it goes over to another one, it hits version 1 there too. So some of the things to note, it's a name-centric configuration, right? If we saw the names that I was giving my application, I was giving it the same name every time, but I was using Istio to manipulate what those names resolved to and where the traffic went under the hood. We can use DNS plugins to create DNS things for us. We can affect how this traffic flows without changing our applications, right? I didn't have to change the host names that my app used. I didn't have to bridge the L3 networks. I didn't have to make VPNs. It's just 2 clusters running in a cloud. I can go through an egress proxy. That makes things nice for NATing, for external firewalls, for legacy network security postures. Everything is encrypted in transit, and all the communication is over the public internet. So I think we're out of time. I do have a section on successful mesh adoption, which I would love to talk with people about. The key point is focus on one pain point, to fix one thing first. If you're going to try and adopt a mesh, don't try and boil the ocean and adopt everything. Pick the one pain point. And with that, I think I'm out of time, although nobody's coming with a crook. So any questions? I know that I threw a bunch of information all real fast. Any questions? Yeah, so are there any big success stories around Istio adoption? There's quite a few that you can look for. Shopify is a good example of a rather large deployment. The weather company, weather.com, the weather app on your phone, is another good example of 2 large, fairly high-profile adoptions that talk about it. There are a bunch more that are not public. It is surprisingly highly adopted, even to us working on the project. One of the weird things about OSS is you don't necessarily get to see all the adoption that occurs. It's a painful problem. But I'm continuously surprised when I talk with people and they go, yes, we are using it. And I go, oh, I didn't know. But those are maybe the 2 highest profile public ones to talk about.
Hi.
Does Istio have a deployment model supporting running the Envoy on VMs or bare metal?
Yeah. So can I use Istio in a way that I can also have like VMs as part of my mesh? So the answer is yes, totally. So it's relatively straightforward and there are scripts that exist today to take Istio, to take an Envoy, deploy it on a VM, and point it at a control plane installation that's on a Kubernetes cluster. The gaps today are actually running the Istio control plane itself on VMs.
Hi. When you show the demo, you were routing manually when one cluster was down and so on. Can you automate this process?
100%. So one of the things that I did not get to talk about here is this is a relatively new feature. It's in alpha in Istio 1.2. There is what is called locality prioritized routing. So one of the configurations that I didn't show you was how we route to that egress proxy. But in effect, Envoy, when it has a set of endpoints, it has a set of IP addresses for a service. Those IP addresses are actually colored with things like the locality of the endpoint, right? So if I'm in a cloud provider, all the nodes are tagged with the locality. Envoy knows its own locality, and Pilot tells it the locality of the things that it's load balancing against. Envoy prefers local traffic to remote traffic. However, as local traffic fails, as part of normal outlier detection, Envoy is going to avoid calling bad backends. It's going to take those endpoints out of rotation, and it's going to start to prefer remote endpoints. And so with this, you can actually get a gradual and graceful flop of traffic over, rather than what I'm showing here, which is effectively a big red button, right? So you would imagine this is the big red button replacement.
What systems does it interoperate with for monitoring and alerting?
Yeah, so what systems does it interop with for monitoring and alerting? There are a slew of integrations. If you go to istio.io, they're called adapters, and there's a full list of all of them. Most of the big metrics backends that you would use, right? So Datadog, FluentD, Prometheus, StatsD, the cloud provider ones. It's a pretty wide range.
Let's leave it at that.
All right, awesome, thank you.